Hello everyone, this is Shashank from Department of Biotechnology and Biochemical Engineering, and today I'll be making a video to explain my ELP101 project where I'll be making analog computers using operational amplifier or OPAMP. So we are going to create an analog computer using an operational amplifier. We are going to discuss what are operational amplifiers, what are analog computers, and in the end we are going to design a small analog computers by ourselves. What is an OPAMP? An operational amplifier or OPAMP is just like any other amplifier which amplifies the input voltage. It has many applications, with analog computers being one of them. As you can see in the figure, it has two inputs, inverting input and non-inverting input, and then in the end it gives out the output Vout. OPAMP has various roles, that it can act as a logical adder, subtractor, integrator, comparator, differentiator in a circuit. An analog computer is a computer which uses to process analog data. Analog computers store data in continuous forms of physical quantities and perform calculation with help of measures. Analog computers are excellent for situations which require data to be measured directly without converting into numerical or codes, such as control system or an aircraft. Now, how does it work? An analog computer operates on input of continuously varying electric voltage. It measures the input rather than just counting it. The examples where analog computers are used, such as thermometer, speedometer, seismometer, or a flight simulator. Now let's come to the most fun part. Let us design a small analog computer to compute sum of inputs. We'll call it the OPAMP analog adder. It would be more fun if we were doing it in lab in real, but since we can't, let's do it on paper and design the circuit and prove it as well. So let's design an analog computer very quickly. This is going to be a very small and very basic analog computer which uses one OPAMP, and it takes three inputs, V1, V2 and V3. So let's draw that very quickly. This is V1, this is V2, this is V3. These are the resistance corresponding to each of them, R1, R2 and R3. This is the input current which we'll see later. And this is here our amplifier, the transistor. These are the three inputs to it. Let's take it V equals to 0 to the ground. And here we have the feedback resistor. And this is the output voltage, right? This is the positive and negative terminals of this transistor. And in just a minute, we have a very small analog computer which computes the value, take three inputs and computes an output V0. Now V0 equals to V1 plus V2 plus V3. This is our claim, right? And now the question comes, how we are going to prove it? Because if it was in a real lab, we would be proving it using the real transistor, real resistor, real voltages. But now since we are not in a lab, let's prove it with help of mathematics. Mathematical proof over here. Now let's use some concepts, okay? The first which we'll use is the virtual ground concept. Here, as you can see, this is the virtual ground, which means here V equals to 0, right? Let's call it VB and let's call it VA, okay? So VA should be equals to VB, and if we know that VB equals to 0, this implies that VA equals to VB equals to 0, right? Let us assume the current over here as IF. Now since we know there's a very high impedance over here, that's why the second point which we have is IN will be equals to IF. Also, if you assume it to be I1, I2 and I3, then we know that IN will be equals to I1 plus I2 plus I3, right? Now let's assume at this junction the voltage will be V0. Let's call it as the junction C, right? And this is the junction A. So we know that VC minus VA will be equals to minus of IF into RF, right? Because the current is flowing from low to high. Now we know that VC is V0 and VA is actually 0, as we saw here, right? Therefore, V0 equals to minus IF into RF. Now this implies that IF equals to minus of V0 by RF, right? And we know that IN equals to IF equals to I1 plus I2 plus I3. This implies that I V naught minus V naught by RF equals to I1 plus I2 plus I3. Right? So let's make it more simpler. We can say that V naught equals to minus RF I1 plus I2 plus I3. Now let's try to get this I1, I2, I3 in terms of V naught, right? Or V in general. So let's do one thing, that we know the voltage here is 0. So it could be 0 here and 0 here. So we can write equation for these three resistance, right? So it would be like V1 minus 0 equals to I1 R1, and similarly V2 equals to I2 R2, and V3 equals to I3 R3. Therefore, we can write this equation, we can rewrite this equation as V naught equals to minus RF into V1 by R1 plus V2 by R2 plus V3 by R3. So we kind of know that we are like almost very near to our proof, but for our easiness, let's assume that R1 plus R2, R1 equals to R2 equals to R3, right? Then it would be V naught equals to minus RF upon R, which would be like common. It would be sum of all the voltages, V1 plus V2 plus V3. And tada, here is our proof. Why this factor is here? Because it amplifies the voltage, right? And we have proved that it adds as well as amplifies the voltage. So now we have created a circuit, a very simple circuit, a very simple adder with help of operational amplifier, and also proved that it's being very functional. But we proved it mathematical, and in future we can also prove it in lab. Thank you.